In the last module, we had said that we are going to discuss what happens when there are finite barriers, but then I had a second thought, and so in this module let us see what happens or how uncertainty principle is manifested by these wave functions that we are now familiar with in particle in a box. Just to recapitulate, these are the things that we have learned so far. The Schrodinger equation is exactly solvable. Boundary conditions lead to quantization. This is the most important lesson that we have got in the last 3 modules. And the other useful rule of thumb that has arisen is that more nodes you have in the wave function, higher is the associated energy. This is going to come handy time and again, especially when we talk later about atomic and molecular wave functions. Then we have talked a little bit about eigenfunction of the linear momentum operator. We are going to revise that once again today. And the reason why particle in a box is interesting and the reason why it is taught in chemistry is that even though it is so simple, it acts as or serves as a very good first approximation for some rather complicated chemical systems as we have seen already. One more lesson that we have got is that when we have more than one dimensions, then we have to perform separation of variable like what we have done between spatial and temporal variables earlier. This is again going to come very handy when we talk about say hydrogen atom. Symmetry and degeneracy go hand in hand. This lesson goes a long way in understanding systems like d orbitals that are degenerate in a bare metal ion, but get classified into 2 groups in tetrahedral or octahedral field and split further upon things like Jahn-Teller distortion. One way of thinking of it is that we are going from a more symmetric to a less symmetric system progressively, and that leads to decrease in degeneracy. As we have seen in particle in 2-dimensional box, the moment we go from a square box to a rectangular box, levels that were degenerate earlier no longer remain so. Also when we talked about 3-dimensional box, we understood that we need a 4-dimensional function x, y, z for the dimensions of the box and the dimension of the wave function itself. So, how is one supposed to draw it? We have exactly the same problem later on when we talk about things like orbitals, but let us wait until then. So, to conclude this part of the discussion, particle in a box model has provided a testing ground for more sophisticated treatment that we are going to see once again later on when we talk about approximation methods. And the question we stopped with in the last module is that what happens if the potential barrier is finite instead of being infinite. But as I said, in this module we are taking a rain check on that, and rather we are going to focus on something that we all know very well, but perhaps do not understand all that well, the uncertainty principle. The product of uncertainties in position and momentum, for example, has to be greater than or equal to h cross by 2. Let us see how this is manifested nicely using the wave functions of particle in a box, and then we will digress a little bit and we will talk about how we will talk a little more about some general aspects of uncertainty principle. So, here goes. Now, we have already learned what the expectation values of position and linear momentum are for particle in a box for nth level. For position, no matter what n is, the expectation value is L by 2. That means, if we perform a large number of experiments, we are going to find that the average of these experiments is going to lead to L by 2. Let us not forget that in each experiment we expect to find a different value of position. It is just that the average value is L by 2, and very soon we are going to define what average value means in a little more formal way. An average value of linear momentum is 0. Does it mean that the particle is not moving? Not really. What it means is that the probability of the particle moving towards positive x direction is exactly equal to that of the particle moving in the negative x direction. So, average value of momentum is 0. But before we go any further, let us make sure that all of us are on the same page as far as the definition of average and standard deviation uncertainty these things are concerned. Then we are going to use them. So, let us go back and let us talk about a little bit of statistics. What is the meaning of mean value? Well, we have learned how to calculate mean value when we were in class 6 or class 7 maybe or maybe earlier, but a more formal definition using probabilities is this, that mean value is summation of j qj multiplied by pj, which means we perform a large number of measurements of the quantity q. For each measurement we get some value. So, j is the identifier of the number of measurements, right. For first measurement j equal to 1, second measurement j equal to 2, 12th measurement j equal to 12 and so on and so forth. So, for every time we get some value. And then let us say we perform a large number of measurements, say 10 to the power 10 number of measurements. Then what will happen is, it is not as if for every measurement we will get a different value. Some values will occur more times, some values will occur less times, and from the number of occurrences we can figure out the probability of a particular value qj to occur. Probability, if we might remember, is nj divided by sum over j nj, where nj is the occurrence of the jth event. Probability is nj, number of occurrence of the jth event, divided by sum over j nj, that means the total number of measurements, total number of occurrences. So, the average value q in angular brackets is equal to sum over j qj multiplied by pj. This is exactly the same thing that we have learnt in school. If we make some measurement 3 times I get 5, twice I get 7, once I get 2. What is the average? We multiply each value by the number of occurrences, sum them up and divide by the total number of occurrences. It is basically the same thing that we have written here. Pj then is the probability of occurrence of the jth event, and it needless to say perhaps that sum over j pj has to be equal to 1, total probability must be equal to 1, okay, and it follows quite easily. You keep on adding all the probabilities, you are going to get sum over j nj divided by sum over j nj, which is equal to 1. Alright. Now let us define something else. Let us define what we have called the expectation value. Expectation value in quantum mechanics of some quantity A is given by integral psi star A psi A hat psi d tau. So, does this expression and this expression, do they mean the same? Actually they do. Why? Because we can think that for every measurement using an operator means using a particular measurement, right, by doing a particular measurement. For every experiment you make this operator operate on psi and you get some value. So, that will come as an eigenvalue equation for that measurement. So, what will you be left with? Aj multiplied by psi star psi. So, we add a large number of that measurements, you get an integral of this sort. Okay. So, essentially the operator operating on psi star psi, that is what the average value or expectation value is. This particular aspect is discussed very nicely in Atkins physical chemistry book. I recommend that we go through it and get our idea clear about what expectation value is. And of course, if the wave function is not normalized, we have to normalize it also by dividing by integral psi star psi. This expression that we have written is valid only for your normalized wave function. In our assignments, we do have some problems where we are required to normalize wave functions and find expectation values. Once we work them out, I think we will be very clear about this. Let us move on. Right now we are concerned not only with the mean value, but also with the uncertainty. So, what is the meaning of uncertainty? Uncertainty is represented by a statistical quantity called standard deviation. But to arrive at standard deviation, it is better to talk about what is called variance first. Variance is defined as sum over j qj minus average value of q whole square multiplied by pj, and it is written as sigma q square. Why? Because ultimately we are going to work with its square root, which is standard deviation. So, let us make sure we understand what we have written here. Let us forget the summation for the time being. Let us only focus on what is there inside the bracket. Let us only focus on this part, Qj minus Q. So, Qj minus average value of Q, what is that? For every measurement, the jth measurement, by how much does the value differ from the average value? That is Qj minus mean value of Q. Suppose I do a summation of this Qj minus mean value of Q. What do I expect to get? Let us say I do something like this, sum over j Qj minus mod average value of Q. Excuse my bad handwriting, especially as I am using a stylus. Well, we can also write Pj here, because we are performing a large number of measurement, we should write probability. So, what we get is the mean value of deviation. What do we expect this to be? For a good distribution, let us say I draw something like this. This is the mean value that is going to remain invariant for all measurements. On x axis I have j, on y axis I have Qj. What do I expect? For one measurement I should get something like this, for the next measurement I might get something like this, another measurement it might be like this one might be like this, and so on and so forth. For a large number of measurement, Qj minus average value of Q for any value of j is this. So, it can be positive, it can be negative also. So, this summation we can expect that it is going to be 0 for a good distribution of data. That summation is going to be 0, but then that is going to be 0 for all measurements provided we have performed a large number of measurements. So, it is useless. That is why we work with the square of it. How does it help if I make a square of it? Then this quantity, let us say square of it is here. I will now use bigger circles. This negative quantity, its square will also be positive, this will be positive, this one will also be positive, this will also be positive. I am assuming that all deviations are less than 1. This is positive, this is also, everything is positive. So, when I do this summation now, what do I get? I get a sum of all these positive quantities, essentially the area under the curve, right. So, that is why it is better to work with sum of squares rather than the deviations themselves. Let me erase this so that it looks a little neater. Okay, now we are all set. So, I hope we have understood what the significance of variance is. Variance would give me a positive number, it is a sum of positive numbers, and smaller the variance better it is, I mean thinner is the spread, but then it is still the square of the deviations. We want to come down to its square root. To do that, let us expand this. Here Qj minus average value of Q whole square is of the form of a minus b whole square, that anybody can see very clearly, and we know that a minus b whole square is equal to a square minus 2ab plus b square. So, let us write that. What will this sum be? This summation over j will be summation over j Qj square minus 2 into Qj multiplied by average value of Q plus average value of Q square, whole thing multiplied by Pj, right. Now, the summation of a sum, summation of a linear combination, let us say, is a linear combination of summations. That is very easily understood, right. So, instead of writing sum over j Qj square minus 2q average value of Q plus average value of Q square multiplied by Pj, I can write it as sum over j Qj square Pj minus 2 sum over j Qj into average value of Q, and when I do that, average value of Q is a constant quantity. So, that average value can come outside the summation, and the third term will be, again since square of average of Q is a constant quantity, it can come out, and the third term will be square of average value of Q multiplied by sum over j Pj. Let us write it. This is what it is, sum over j Qj square Pj comes from the first term here minus 2 average value of Q, average value of Q as we said is a constant quantity, will come outside the summation sign, average value of Q multiplied by Qj multiplied by Pj plus, again square of average value is also constant quantity, it will come outside the summation, square of average values or square of means multiplied by sum over j Pj. Now see, we can simplify this without much of a hassle, because we have defined already that sum over j Qj Pj is equal to the mean value of Q. So, the second term immediately becomes minus 2 mean value of Q multiplied by mean value of Q, or in other words minus 2 into square of the mean value of Q. What about the third term? Sum over j Pj equal to 1. So, the third term reduces to square of mean value of Q. What about the first term? The first term is sum over j Qj square Pj. Now, look at this definition of mean value of any quantity, that it is sum over j Qj multiplied by Pj. Now, instead of Q, if I wrote Q square, then this summation would be sum over j Qj square Pj, and that is exactly what we have here. So, this turns out to be the mean of squares of Q. So, the difference between this and this needs to be understood. What we have here is square of means, what we have here is mean of squares, they are not one and the same. It is trivial for us to work out, take any set of numbers 2, 3, 5, 6, 7. So, why did I eliminate 4? 2, 3, 4, 5, 6, 7. Work out the mean and take its square. On the other hand, take squares of each numbers and work out the mean of these squares of numbers, they are not going to be the same. Okay? And that forms the basis of the definition we are heading to. So, now let us write the expression for sigma q square. What does it reduce to? The first term reduces to mean of squares of q, second term reduces to minus 2 square of mean value of q, third term reduces to square of mean value of q. So, we are going to get mean of q square minus 2 multiplied by square of mean value of q plus square of mean value of q. Of course, minus 2 plus 1 is equal to minus 1. So, this reduces to a very simple expression, difference between the mean of squares and square of means, that is variance. Standard deviation is the square root of variance. So, that then turns out to be square root of mean of q square minus square of mean value of q. So, that is what we have arrived at, something that is pretty well known, and one can study these from well any textbook. Macquarie and Simon is a physical chemistry textbook that has discussed it in some detail. So, one can actually look at that. So, now the stage is set for us to go into the study of to understand what is the uncertainty. Uncertainty now means standard deviation in position. What is the uncertainty in momentum, linear momentum for a particle in a box. So, I think what we will do is we will talk about uncertainty in position and then we will take a break. In the next module perhaps we are going to talk about uncertainty in momentum and continue from there. Let us see, depends entirely on how much time we spend on the next part of the discussion. Alright. So, what is uncertainty in position? By the definition that we have just constructed. Uncertainty in position is square root of the difference between mean square position and square of mean position. And out of these two quantities we know one already. We know that the mean position, which is this mean value of x for particle in a box, is L by 2, that is established previously already. Now let us work out what is this average value of squares. That will take a little bit of time and we are going to use integration in parts. Since we do not know who is there on the other side of the camera, what is the level of mathematical preparation, I am going to go slow in this part and we are going to show you every step of this. We actually used integration by parts already, but then that time perhaps I went a little fast. So, let us make up for that by showing every step in this one derivation. Later on when we use integration by parts, I am going to jump steps. Alright. So, average value of squares x square is equal to 0 to L x square multiplied by the square of psi nx dx. This is from the same expectation value that we have got. The operator here is x square, which simply means multiply by x square. It is as simple as that. To go further, we are going to need to use the expression for the wave function, and this is what it is. Psi n of x is equal to root over 2 by L multiplied by sin n pi x divided by L. This is something that we know very well already. Right, let us plug in that expression, then this is what we get 2 by L because sin square psi square, right. So, since it is psi square, 2 by L root 2 by L multiplied by root 2 by L is 2 by L, comes outside the integration. Integral 0 to L x square sin square n pi x divided by L dx. Now, when we have an integration like this, then usually we like to simplify it by going from the square of trigonometric term to something that does not have a square. And the formula that one can use very easily in this case, once again going back to class 11 mathematics, is the formula that we want to use is cos of 2 theta is equal to 1 minus 2 sin square theta. I think all of us would actually know this formula, cos 2 theta equal to 1 minus 2 sin square theta. So, what is sin square theta then? Sin square theta is not very difficult to see, is half multiplied by 1 minus cos 2 theta. So, here what is theta? Theta is n pi x by L. So, by substituting we get something like this. The integral becomes integral x square 1 minus cos 2 n pi x by L. This was n pi x by L. So, 2 n pi x by L, and there is a half outside, that half has cancelled this 2 in the numerator. Okay. So, this is what we have got. Now, let us simplify this a little bit. We will write it as a linear combination of two integrals. First one is very simple, 1 by L integral x square between limit 0 and L. Second one is minus 1 by L integral 0 to L x square multiplied by cos 2 n pi x by L dx. So, what we can do is we work out the first one quickly. That is very simple, I do not even have to say perhaps. X square integrates to give you L cube by 3 between limit 0 and L, and then of course in the next step L cube by L will be written as L square. So, this first integral essentially becomes L square by 3. What about the second one? We write the second one as minus 1 by L 2 n pi multiplied by integral 0 to L x square d dx of sin 2 n pi x by L dx. Now, why did we do that? First of all, let us convince ourselves that this is correct. What is d dx of sin 2 n pi x by L? We expect a 2n pi by L outside, we do not have it, that is why we have written L by 2n pi, that part is fine. But why do we have to write it in this manner in the first place? Because the formula for this integration by parts is this integral. Well, since we are doing a standard integration, we have written the formula for standard integral also, well not standard, definite integration. We have used the formula for definite integral as well. Integral between limits L1 and L2 u dv dx into dx, right, dv dx, that is why we have to write it as dv dx. U into dv dx dx is equal to product of u and v, substituting the limit L2 minus product of u and v for the limit L1, okay, minus integral L1 to L2 v du dx dx. So, as you can see, we will have to do it in one more step, that we will come to later on. But right now what do we have? The first term has become L square by 3, and using this formula we can expand the second term by using integration by parts. What do we have here? Integral x square d dx of sine 2n pi x by L dx. So, u is equal to x square, v equal to sine 2n pi x by L. There is a definite recommended order of priority when one performs integration by parts. The algebraic terms, polynomials, have highest priority for being used as u. The trigonometric functions come second. That is why we have used u equal to x square and not v equal to x square, alright. But all that is well 11-12 level mathematics. So, let us go ahead, let us work out what is uv at limit L2 minus uv at limit L1. What is the limit L1? 0. So, what is the value of u? U equal to x square. So, for the limit L0, this uv is going to be 0. So, the second term here is going to be 0. First term is u multiplied by v for L2. For L2 x equal to L. So, x square is L square, no problem with that. But v is sine 2n pi x by L, that is sine 2n pi. What is that? 0. So, this uv at L2 minus uv at L1 essentially becomes 0 minus 0. What about the second integral? V equal to x square and u equal to x square. So, du dx becomes 2x and v is simply the sine term here. So, this is what we get minus 2x sine 2n pi x by L dx. So, clearly once again we have to do integration by parts, okay. So, we try to do that. Before that we clean it up a little bit and we get L square by 3 plus 1 by n pi integral 0 to L x sine 2n pi x by L dx. And now it is simple because we have done it once already. So, I leave it for you to do it yourself and convince yourself that this is the result we get, okay. We will go to the next one. So, when we do integration by parts again, this is what we get, integral 0 to L x d dx cos of 2n pi x by L dx. Go to the next step, again this time what will happen is v is equal to a cos term, right, v is equal to a cos term and cos at x equal to L, cos 2n pi x by L is actually equal to 1 and x equal to L there. So, the first term is not 0, first term is L. The second term is still 0 because you are multiplying by x, which is 0, and then we get this integral cos 2n pi x by L dx, which is now everybody knows how to work this out and we will do it, and we use the conditions that we have learnt already, that at the boundaries the wave function is equal to 0. Remembering that the wave function is essentially the sine term, we get L minus 0 inside the bracket and we get L cube by 3 minus L square by 2n square pi square. This is the what have we worked out then? Let us not forget that we have worked out the average value of x square. What are we looking for? We are looking for the uncertainty or standard deviation. square root of average value of x square minus square of the average value of x. This is what we are looking for. So, let us stop here. In the next module we are going to start from here and then we will get the final expression. After that we will work out the expression for the uncertainty in momentum and we will convince ourselves that their product is indeed greater than h cross by 2.